Hello guys, welcome back to EC TechNest. Today in day 31 of the Verilog digital design series, we are going to talk about Baugh multiplier. In the previous lecture, we discussed about combinational multipliers, and in today's lecture, we'll be discussing about Baugh multiplier. It is a specialized hardware algorithm designed for signed multiplication using 2's complement representation. In the previous lecture, whatever we discussed was unsigned multipliers. That means it did not have any negative numbers. In this Baugh multiplier, it's all about signed multiplication. This was first proposed by Charles Baugh and Bruce Wooley in 1973. It is widely used in digital signal processing because it eliminates the need for complex sign extension logic, making it faster and more regular than standard array multipliers. When we multiply two signed numbers, the MSB has a negative weight. In a standard multiplier, this requires you to subtract certain partial products. The Baugh-Wooley algorithm mathematically rearranges the multiplication equation so that all partial products can be added together. What we mean to say here is, for an example, if we are doing a multiplication between two signed numbers, the last MSB bits will have signed values. That means it will have minus like that. So what will happen is whatever the partial products are produced by these bits will have negative sign. To avoid that, what we'll do in the Baugh multiplier is we'll give them a complement. In a standard n cross n signed multiplication, the partial products formed by the sign bits have negative weights. Simply adding them as if they were unsigned would lead to an incorrect result. So as we discussed, whatever the signed partial products will get, we needs to be changed. If we just add them using full adder, we'll get incorrect result. So, what does the Baugh solution give? The algorithm transforms the negative terms into positive ones by inverting specific partial product bits. These involving the signed bits of the multiplier and multiplicand. Adding constant values at specific bit positions to correct the bias introduced by the inversion. So, we'll discuss the first inverting part in the next slide. This adding of the constant values will be discussed in the last slide. So to understand the hardware architecture, we need to understand something called as processing engines. This will be called as a processing engine. We'll discuss about it in detail. First, we'll see what it is. Partial product generation using standard AND gates for the magnitude bits. So what you will do is, if your partial products have both unsigned values, that is magnitude bits, you will use AND gates. If you have signed partial products, you will use an AND gate. Regularity. Since the layout is very uniform, consisting of grid of full adders, it makes ideal for VLSI chip design because the tiles can be repeated easily. Here, whatever you are seeing here will be replaced with these full adders. So it is very easy to multiply and write the code. Also, it is very easy for making the chips. So whatever your carry is going to be left at the bottom is going to be added using a carry save adder, often used to sum the partial products to reduce the propagation delay followed by a final vector merging. So whatever carry you get at the end of the addition will be solved using a carry look ahead adder or a carry save adder. This is your architecture. This is how your Baugh multiplier looks. So for whenever you have a n bit signed numbers, that is a and b, you will get it in this form of the equation. This equation you have to remember it. So let us see how we get that equation. Considering x is your input and y is your input, we have 4 bits: x3, x2, x1, and x0. y3, y2, y1, and y0 are your other inputs. P7 to P0 will be your final output, that is 8-bit output. Because these are in the 2's complement form, we can compute their numerical values as. So you know that at the end of the x values, you will have an MSB bit. So we'll convert this into this equation form. Now that I know this P is the output, P is nothing but x into y, product. So I solve this and I'll get this final equation. This is only for mathematical calculation to understand how the algorithm works. But To understand how the digital design architecture works, we need to understand in depth about the multiplication part. Now you've seen that it is a 4 bit into 4 bit multiplication. So you have to get 16 partial products. All the 16 partial products are mentioned here. And one thing to note here is all this A3 B0, A3 B1, A3 B2, A2 B3, A1 B3, and A0 B3 are signed partial products. That means they'll have negative weights. How this is going to be solved, we'll see. Let us take a small example. Minus 5 into 2. Your answer should be minus 10. So what we'll do is, first, since minus 5 is the negative number, we will take a ones complement of that. First, we'll convert it into binary form. 0 1 0 0 1 0 1 is the binary for plus 5. We'll get a ones complement of it, that is 1 0 1 0. We'll add a 1 to it to make it into two's complement. Now that we have our two's complement form of 5, and 2 is however positive, so we do not need to convert it, we just need to write it as it is. Now we have 1 0 1 1 0 0 1 0. You need to multiply it. 0 into all the terms will give you 0 0 0. 1 into all the terms will give you 1 0 1 1. Same here, 0 0 0 0 0 0. Now what we need to do is we need to add it. Here in this first you will have 0. 0 and 1 will give you 1. 0 and 1 and 0 will give you 1. All are 0, so 0. Here you have 1. Here it is 0. And here also it is 0. So what happens is you will not get this last extension bit. This is important because this is the one bit that is going to tell you whether it is plus or minus. So what we need to do is we need to extend this. So if you have last MSB as 0 for the partial product, we'll continue it 0 0 0. Here we had 1, so we'll continue again the same. Here you had 0, we'll extend it. So at the final product, we'll be left with 1. So P7 is 1. So you get minus 10 as your answer. Now we'll understand about processing engine. There are two types of processing engines, white cell and gray cell. So processing engine is mainly categorized into white cell and gray cell. So white cell is used for unsigned bits and gray cell will be used for signed bits. That means if you have partial products that are you having the A3 or B3, you will use gray cell. And for partial products, like see in this example you can understand, whatever is not circled will have white cell as the processing engine. Whatever is circled, that means your signed partial products will have this gray cell as processing engine. Now that you have seen, we'll see how the architecture is actually. So here you can see that a naught will go for all the processing engines as input. Only for the last bit will give a negation, that is a naught bar. Same way for all these rows also, these columns. And now we'll give inputs b naught, b1, b2, b3. Here one thing that you have to notice, when you are giving here, it will be a gray cell because is involving a3. Whenever this bit is being involved, you'll use a gray cell. Other than here, I'll tell you why this is not having that. So you will have three gray cells, six gray cells, and others will be white cells. Now that you will give your inputs here, that is whatever your 4-bit input you had, that you will give, and Cin will be given as 0. Here, two things that you want to notice here: the B3 A3 term. This is not a gray cell. You might question why. And also here, I have connected the B3 to C. That means my carry is getting connected again to the input B3. Let us see why. Why the connection to B3? See, in the Baugh array, the partial products are AI BJ for all middle bits, and inverted bits will be A3 BJ or AI B3. Special condition is A3 B3. This one, what we are talking about, A3 B3. So, where do we need to give the constant? In the first slide, I mentioned that we'll be using a constant, right? Adding constant values at specific bit positions to correct the bias introduced by the inversion. So whatever, when we are doing this Baugh multiplication, while this inversion process is taking place, we introduce a bias. See, here only you can observe. Here, when we are doing it, this A3 bar was not actually needed, but we have done it because we have given all the inputs in the same way. So to avoid these bias conditions, we need to give constants. In your zoomed in image, you have a small loop at the bottom right. This loop. This is where you inject the first constant one. Now connecting that C to loop to a logical high one, this adds the necessary one to the carry ripple chain to the bottom row. So when you are doing your carry ripple adder here, it will give the necessary carry ripple chain to continue the addition of the carry to the next bit or else the next full adder. The left side constant, that means we're talking about this side. Here we need to give one constant 1. The carry out of the bottom left processing engine is typically added to a 1 to produce the final P7. So this is going to be the out when you're talking about output. P7 needs to be a signed bit if you want to get a product like minus 10. See here, to get minus 10, this was very much required. So that is why we add this constant 1. See, here is the correction that you can observe. Here we are adding correction when added here to handle partial products. Carry connection here. See, this is the carry connection that we are giving from one filler to another. It ensures that the two's complement for subtraction. That means when we are added here, this also is required, right? Plus 1. So that is why we have added that. And correction 1 implicitly for adding the sign bit. That is for P7 to require, we need to give a constant 1. Efficiency handles signed numbers natively without extra conversion steps. Speed is faster than shift and add or Booth's algorithm for smaller bitwidths because of its parallel nature. Compared to our previous lecture where we discussed about combinational multipliers, this is much faster and it can also handle signed numbers. And one thing that you can see is we are using all full adders with AND gates and NOT gates. So it is very easy to replicate and is easy for wiring and area on a silicon chip. Complexity for a very large bit width, example 64 bit, the area gate count grows quadratically. That means n square, which can be costly compared to the Booth's algorithm. So this is one advantage and disadvantage when we talk about Baugh multiplier. If you have any doubts, feel free to put it down in the comment section and link to the playground will be given in the description.